Differently from the standard nucleotide substitution models, POMOs feed on allele frequency data. So essentially, we have to tell whether the site is polymorphic or fixed. And we tend to organize these allele frequency data using count files. Count files have, of course, universal features that I'm representing here. At the first header line, we just write the name of this file, count file, and then we indicate the number of taxa that we have in our alignment and the number of sites in our alignment. So it is telling me that there are 3 taxa and 5 sites. Let's see if this is true. I have 3 taxa and there are 5 sites in my alignment. At the second header line, we state the genomic location of the sites, so the chromosome and the genomic position, and then right following this we have the names of the 3 taxa in our alignment, in this case Gorilla Graweri, Gorilla D. Helgi, and Gorilla Gorilla. All the remaining rows include information about the specific chromosome at which the site is, the specific genomic location at which the site is, and the allele frequencies. And the allele frequencies are representing using these counts or count patterns that we use. For example, the count file is just this bit here, and we know that all the counts for the different alleles that we have in our population are separated by commas. So by just looking at this allele count, I can tell immediately that there are 4 alleles in my population and only one of them was observed, which was the first one. So which was this allele? So I will tell you these counts were organized following this order A, C, G, and T. So I know that at position 4000 for this specific position in chromosome 1, the gorilla Berinjei Graweri has an observed fixed site of the type A, and this is what I'm observing here. But of course we can also observe polymorphic states, and at chromosome 19 in the specific position for the population gorilla gorilla gorilla, from the 54 individuals that were sequenced, 10 had the A nucleotide, however 44 had the G nucleotide, and this is of course a polymorphic state. There are 2 aspects that I wanted to comment about the count files. The first one is that we put npop, although this represents the number of taxa, and this npop terminology comes from historical reasons, because the first applications we did for POMOs were mainly using populations, but of course we can use any systematic unit that we might be interested in, like species, populations of course, subspecies, community, or even combinations of different systematic units. It really depends on the question that the researcher has and what history he wants to solve. Another thing is that for some systems we might not have information about the karyotype, so we might not know in which chromosome it is or at which genomic position these sites in our alignment are. So in this case we can just replace this information using NA or any other word actually, because this information is not used for inference. Of course it's quite handy to have this information because we might want to do inferences just using one chromosome or excluding the sex chromosomes, or doing inferences in a certain specific region of the genome. So of course having this information is handy, but it's not necessary, so you can just put any other word here instead. Another important thing about the count files is that the order of the alleles matter. And why it matters? Because it will determine the order of the parameters that I'm estimating. For example, in this case, all the allele counts in this count file follow this order, A, C, G, and T. And as a result, the estimated parameters will follow this order. So this is the order of alleles that I have in my allelic counts, and immediately I know that the vector of fitness coefficients will follow this order. So at the first position, so the fitness coefficient will be relative to the A allele, and the last one, for example, will be relative to the T allele. The same thing happens to the base composition or the base frequencies pi. They follow the same exact order as in the allelic counts. For the base exchangeabilities, we organize it in a slightly different way because we have to account for all the pairwise combination of alleles. So what we do, we just take the first one and combine it with the second one. So AC, rho AC, this is the first position. The second position of the exchangeability vector will include A with G, so the first allele with the third, the first allele with the fourth, and so on and so on. For the mutation rate, so if we do not use reversible mutations, we will not have the pi and rho vectors. Instead, we'll have a single mu vector. And this is the mutation rates. So what we do, we follow more or less the same rationale for the rho vector, for the exchangeabilities, but of course we have to also account for the back mutations. For example, the first one, we consider the mutation rate from A to C, so the first allele with the second, but then we have to immediately represent the C to A. So at the second position, I have the back mutation. Again, I use the mutation rate from A to G, so the second combination, and the back mutation, and so on and so on. Of course, the two last positions in the mutation rates vector will be the mutation rates from G to T, and then from T to G. So of course, these order matters to know at each position some parameters that I might be interested in are located. And this is important because I might be interested in determining whether is there some, for example, mutational bias towards G and C's, for example, and I wanted to know what is the base composition, if it's heterogeneous or homogeneous, and I wanted to know which nucleotides stand out from the base composition vector. I might be interested in determining what's the fitness coefficients and if they are really different or close to neutrality. So it is important to know which order these vectors that will be estimated at the end follow, and this is essentially a way of doing it. Of course, if you have a different allelic counts, this will change, but the rationale is essentially explained here.